Welcome dear learners. We are studying quantum chemistry and in this module we are discussing a particle in a ring problem. The contents of this module are spherical polar coordinates, Schrodinger wave equation in spherical polar coordinate, particle in a ring description, the phi equation, the solution to the phi equation, the graphical representation of energy and wave function, and examples. First of all, the spherical polar coordinates. For systems like particle in a ring, rigid rotator, hydrogen atom problem, etc., it is more convenient to express the Schrodinger wave equation in spherical polar coordinates. The spherical polar coordinate system consists of three variables. They are r, theta and phi. We can move on to the details of that in coming slides. This expression in spherical polar coordinate is mainly because of the fact that the attractive force has spherical symmetry depending only upon the value of r. This is a pictorial representation of spherical polar coordinate. There you can see the presence of three variables. They are r, theta and phi. The angle theta is called co-altitude and the angle phi is called azimuth. Now we can enter into details of the spherical polar coordinate system. Now consider the three coordinate axes. For convenience, I am representing this as y-axis. This is the z-axis and this represents the x-axis. This is being the origin and consider a point P here. Consider a point P and the P can be represented as P of x, y, z. Since its position is represented by three variables x, y and z, I mark the point P as P of x, y and z. Now consider the distance OP, that is the distance from the origin to the point P. The distance from the origin to the point P is taken as small r, that is the first variable in the spherical polar coordinate system. Now it should be noted that there is an angle between z-axis and the line OP or r. That angle I mark as theta. So theta is the angle between z-axis and the line OP or small r, and this is theta. So now we described two parameters, two variables, r and theta. There is one more variable in spherical polar coordinate system. The variables are, the next variable is phi, and in order to find out phi, we have to make some arrangements here. Now I am taking the projection of P on the xy plane. Projection of P on the xy plane. Let the projection of P in the xy plane is like this. This is the point. This is the projection. And this point I mark it as Q. And this line PQ is parallel to the z-axis. The line PQ is parallel to the z-axis. Now we can assume a plane containing z-axis and the line PQ. This is a plane, imaginary plane that contain the z-axis and the line PQ. That plane makes an angle phi with the x-axis. That plane makes an angle phi with the x-axis. Therefore, we got three variables described like this. The distance from origin to the point P is taken as r. The angle between line r and z-axis is taken as theta, and the angle between x-axis and a plane containing z-axis and the line PQ is termed as phi. So we have three variables, that one is distance, that is r, and others are two angles. The two angles are theta and phi. Thus, in spherical polar coordinate system, instead of x, y and z, we have three variables r, theta and phi. Now, we have to study or understand the relation between the Cartesian coordinate, say x, y and z, with the new coordinate system, that is the spherical polar coordinate system. The relation is like this. X is given by x is equal to r sin theta cos phi. Then y is equal to r sin theta sin phi, and the last term z is equal to r cos theta. So, this is the relation between the Cartesian coordinate and spherical polar coordinate. This should be very important and keep in mind for further study. Now, this is the pictorial simplest representation of the spherical polar coordinate, and as I mentioned, r is the distance from origin to the point, and theta and phi are also shown here, and we have to look into the range of these three variables, and it should be noted that the range of variable, first of all r must be 0 less than or equal to r, or r is always greater than 0, or sometimes it may be equal to 0. And the value of phi is like this, the range of phi is like this, 0 less than or equal to phi, less than or equal to 2 pi. That is the maximum limit of phi is 2 pi. That is, phi ranges from 0 to 2 pi. And pi, that is another term. Pi is 180 degree, and we can find out the range of theta like this. It is from 0 to pi. 0 to pi. That is, the range can be represented like 0 less than or equal to theta less than or equal to pi. So, theta ranges from 0 to pi, phi ranges from 0 to 2 pi, and r ranges from 0 to any higher value or 0 to infinity. That about the situation. Now, the Schrodinger wave equation in spherical polar coordinates. We have the time independent Schrodinger wave equation as h hat psi is equal to energy into psi. It is noted that h hat is an operator or the total energy operator, that is called the Hamiltonian operator. H hat is given by minus s cross square by 2m del square plus v. The first part represents kinetic energy and the second part represents potential energy. Hence, h hat is called Hamiltonian operator or the total energy operator. In spherical polar coordinates, the time independent Schrodinger wave equation can be represented like this. This is the Schrodinger equation. Here we can see the presence of the variables r, theta and phi instead of x, y and z in the time independent Schrodinger wave equation. That is, we switch over from the Cartesian coordinate to the spherical polar coordinate, and this is the Schrodinger equation, that is 1 by r square into dou by dou r of r square into dou psi by dou r plus 1 by r square sin theta dou by dou theta sin theta into dou psi by dou theta plus 1 by r square sin square theta dou square psi by dou phi square plus 2m by s cross square. This term can also be represented like this. This is also equal to 8 to pi square m by h square, because h cross equal to h by 2 pi. So, if I put h cross equal to s by 2 pi, I will get 8 to pi square m by h square instead of 2m by s cross square. So, this is the into that term into e minus v into psi is equal to 0. Here psi depends on three variables, so I can put r, theta and phi, psi of r, theta and phi. Okay. So, this about the Schrodinger wave equation, time independent Schrodinger wave equation in spherical polar coordinate system. Now, we are moving on to the present discussion, that is the particle in a ring problem. First of all, description of the problem. Consider a particle of mass m that is executing rotational motion in a circular path and radius of the circular path is small r. radius of the path is small r. M is the mass of the body, it executes rotational motion or circular motion, and the radius of the circular path is small r. It should be noted that polar coordinates, that is spherical polar coordinates, are better logical choices to model this system. That means the Schrodinger wave equation and related parameters can be expressed in spherical polar coordinates more conveniently for the particle in a ring problem. Now, to solve this system on a quantum level, the Schrodinger equation must be expressed in polar coordinates. The Hamiltonian operator describing the present system. And we know the Schrodinger wave equation is a Hamiltonian psi is equal to E psi, and the Hamiltonian operator describing the present system is like this. S cross equal to minus S cross square by 2m r square into d square by d phi square plus v. Here in this Schrodinger, in this term, in this Hamiltonian operator, we can see that there are two variables, that is on r variable and another one is phi variable, and another one is phi variable. But r is taken as a constant, and we know the fact that moment of inertia I of a body is given by I is equal to mr square. Therefore, the term in the denominator, that is mr square, can be replaced with the I. This is possible because we already mentioned that the radius of the circular path is a constant r. Hence, this term can be taken as a constant. So, the Hamiltonian operator is minus s cross square by 2i d square by d phi square plus v. Hence, this equation, this Hamiltonian operator has one and only variable, that is phi. So, the Schrodinger equation also contains one variable, that is phi. Hence, the Schrodinger equation for a particle in a ring problem is considered as a phi equation because the Schrodinger equation contains only one variable. Now, the Hamiltonian operator describing the present system is already mentioned. H hat equal to minus s cross square by 2i d square by d phi square plus v. V represents the potential energy of the system. We have H hat psi is equal to E psi. Substitute the value of the Hamiltonian operator here. That is minus s cross square by 2i d square phi divided by d phi square is equal to energy into phi. And this is possible because only one part, only one variable, that marked as phi. So, d square phi divided by d phi square is equal to minus 2i divided by s cross square into phi, or the wave equation, the Schrodinger wave equation, that is simply a phi equation because the wave function has only one component and that component is the phi. Therefore, psi is replaced with the phi, and hence we got the final Schrodinger wave equation for a particle in a ring problem as d square phi by d phi square plus 2ie divided by s cross square into phi is equal to 0. It should be noted that the term big phi, capital phi, represents wave function of a particle in a ring. That is the final equation once again d square phi by d small phi square. That is differential of this capital phi with respect to small phi. Small phi is the variable and the capital phi is the wave function. So, d square phi divided by d phi square plus 2ie divided by s cross square into phi is equal to 0. Into phi is equal to 0. This about the Schrodinger wave equation for a particle in a ring problem. Now, we have to get solution to the phi equation. The Schrodinger wave equation for a particle in a ring problem is d square capital phi divided by d phi square plus 2ie by s cross into phi is equal to 0. The acceptable solution of this kind of second order differential equation can be adopted from mathematics. That is, phi is equal to capital A into e raised to im phi. Here A is a constant and later it can be seen that it is equal to the normalization constant, and m is another constant, and A and m are to be determined. So the solution is phi is equal to a into e raised to im small phi. Now the boundary conditions. The boundary conditions are very, very important as far as the variable phi is concerned. It should be noted that the Schrodinger equation contains only one variable phi. Therefore, we have to think about the boundary condition or the variation of phi. The boundary condition for this system is called the cyclic boundary condition. In that, the function phi must have the same value after one revolution. One revolution means 360 degree. 360 equal to 2 pi radian. That means the value of small phi at phi degree equal to value of phi at phi plus 2 pi, that is phi at phi equal to phi at phi plus 360 degree. 360 degree means 2 pi. That is, one revolution is completed. This graph also represents phi 0 and phi 2 pi. This is value phi at 0 degree, and the last one is the value phi at 2 pi. 2 pi is after a revolution, after 360 rotation. 360 degree rotation is simply known as one revolution. So, one revolution will not alter the value of phi. That implies phi of phi equal to phi of phi plus 2 phi. This is graphically shown here. Now, normalization of the wave function. It should be noted that the acceptable solution to the phi equation is phi is equal to a into e raised to im phi. And we have to normalize this expression to evaluate the value of a. And the normalization procedure, we already learned that the general equation for normalization, integral psi star rt psi of rt d tau must be equal to 1. Limit of integration is from minus infinity to plus infinity. For the present system, psi of rt is equal to phi. That is a into e raised to im phi. And psi star rt, that is the complex conjugate, that is equal to phi star. That is equal to a into e raised to, in order to get to the complex conjugate, what we have to do is replace I with the minus I. So, I got e raised to minus im phi. This is phi and this is phi star. And think about the limit of integration. It should be noted that the integration limit ranges from 0 to 2 pi. This is because the condition, the boundary condition for phi is 0 less than or equal to phi less than or equal to 2 pi. This we already learned with the spherical polar coordinates. Therefore, the limit of integration here is from integral 0 to 2 pi, integral 0 to 2 pi, phi star phi d tau, phi star phi d tau. D tau is nothing but d phi, and this must be equal to 1 as per the condition of normalization. Substituting the value of phi star and phi here and integrate, we get 0 to 2 pi. A is constant in both the sides, so I can put a square outside. E raised to minus im phi into e raised to plus im phi d phi. A raised to m into a raised to n, a raised to m plus n. These two terms vanishes, and the result will be, this RHS must be 1, and on integration we are getting a square into integral 0 to 2 pi d phi must be equal to 1. Integral 0 to 2 pi d phi. Integral d phi is equal to phi. Upper limit minus lower limit produces the value 2 pi. So we got a square into 2 pi equal to 1. That implies a square equal to 1 by 2 pi. Hence the normalization constant a is equal to 1 by root of 2 pi. I can put the value of a here to get the complete normalized wave function as phi of phi or capital Phi is equal to 1 by root of 2 pi into e raised to im small phi. This is small phi variable, this is phi of phi the wave function, this is normalization constant, and this is the normalized wave function of a particle in a ring problem. Now, expression for energy. We have the normalized wave function phi or phi of phi is equal to 1 by root of 2 pi into e raised to im phi. We can find out energy by proceeding as follows. First of all, we have to differentiate this phi twice with respect to small phi. So we have a phi is equal to this one, and from this I can write d phi by d small phi. That is, I am going to differentiate this with respect to phi is equal to 1 by 2 root of 2 pi can be taken as a constant, 1 by root of 2 pi into differential of e raised to x is e raised to x itself. So e raised to im phi into im. This is the value of d phi by d phi. And see this function, this part is simply again phi. So the result I can put as capital phi into im. Capital phi into im. Now we have to evaluate d square phi divided by d phi square. This is theoretically d by d phi of d phi by d phi. That is, we have to differentiate it twice. D phi by d phi is already evaluated. That is equal to phi into im. This is equal to d square phi by d phi square is equal to d by d phi of d phi by d phi. D capital phi by d small phi is already proven as equal to capital phi into im. Capital phi into im. Therefore, I got the result d phi by d phi of im. D phi by d phi of im. D phi by d phi. D phi by d phi, that is already equal to phi into im. Again into im. That is minus m square capital phi. Minus m square capital phi. This is because im into im, that is equal to I square m square multiplied with the capital phi. But I square is equal to minus 1. Therefore, minus m square capital phi. Thus, I got the relation d square capital phi divided by d phi square equal to minus m square capital phi. Or this negative term can be moved on to the left side. Or I got d square phi by d phi square plus m square capital phi is equal to 0. This relation I got from differentiation and rearranging of the original normalized wave function. So I now got this relation. Now we got this relation d square phi by d phi square plus m square phi is equal to 0. We got this relation that we already proved now. But we have the Schrodinger wave equation for a particle in a ring. In the initial part of the discussion, we have done it. And we have the Schrodinger wave equation for a particle in a ring as d square phi by d phi square plus 2ie by s cross square into phi is equal to 0. And now we go to this relation. Previously we have this relation. On comparing these two relations, it is clear that the term m square is equal to 2ie by s cross square. So on comparing 1 and 2, we get m square equal to 2ie by s cross square, or minus m square is equal to minus 2ie by s cross square. We can cancel negative on both the sides, or simply we are getting on comparison m square is equal to 2ie by s cross square. On rearranging, we get the value of energy. The energy value is equal to capital E equal to s cross square m square divided by 2i, where m may be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Thus, energy of a particle in a ring problem is given by the expression capital E is equal to s cross square m square divided by 2i. Now, the graphical representation of energy. We have energy E is equal to s cross square m square by 2i, where m is equal to these values. By putting different values for m, we will get several energy levels. If I put m is equal to 0, the energy also equal to 0. That is m summum 0, m is equal to 0, energy also 0. Now, m is equal to minus 1 or m is equal to plus 1, will get the same result. That is E1. E1 equal to s cross square by 2i. Similarly, if you put m is equal to minus 2 or plus 2, same energy is obtained, and that energy E2 is equal to 2s cross square by I. And if we are having m is equal to plus or minus 3, again we get the energy as doubly degenerate, or two energy levels are there. E3 equal to 9s cross square by 2i. So these are various energy levels of the particle in a ring problem. Now, the graphical representation of wave function. We have the wave function for a particle in a ring problem as phi is equal to 1 by root of 2 pi into e raised to im phi, where 1 by root of 2 pi is known as the normalization constant. Here, m is equal to 0, plus or minus 1, plus or minus 2, etc. If m is equal to 0, the amplitude is constant, that is height is constant. And for higher energy state, the number of nodes increase. Node is the region where probability of finding the electron is equal to 0. And this represents the arrangement of wave function, and that one represents that of probability, arrangement of probability. This is for m is equal to 0. This is for m is equal to plus or minus 1. And the next level corresponds to m is equal to plus or minus 2. Hence, this is the pictorial representation of wave function, and its square, that is nothing but the probability. Left hand side is wave function, and the right hand side represents corresponding probability plot. Now we are having example for a particle in a ring problem. The molecule benzene can be thought as a system of electron on a ring problem. That is, the molecule benzene can be considered as a system of a particle in a ring problem. That is, the radius is taken as 1.4 angstrom, and in benzene, homo-LUMO transition. Homo represents highest occupied molecular orbital. LUMO represents lowest unoccupied molecular orbital. These are two nearby energy levels in the benzene molecule, and the transition of an electron from HOMO level to LUMO level produces absorption of some wavelength, and that wavelength will be the longest wavelength. That is, that transition is the minimum energy transition. By applying the concept of particle in a ring problem, the longest wavelength can be calculated using the expression for energy of a particle in a ring. And for that calculation, we have to put the value of m as m is equal to 2 for higher energy level, that is LUMO, and m is equal to 1 for lower energy level, that is HOMO. So, if we are putting m is equal to 1, we got the level E1. And if we put m is equal to 2, we got the level E2. So, the energy difference can be taken as E2 minus E1. E2 minus E1 is equal to s cross square 2 square by 2i minus s cross square 1 square by 2i, that is equal to s cross square by 2i into 4 minus 1, that is 3s cross square by 2i. By substituting necessary values in that expression, we got delta E or energy separation. That energy separation can be converted to wavelength, and that wavelength value obtained will be equal to 213 nanometer. And this wave number is in good agreement with the observed longest wavelength for benzene molecule. Thus, in the present discussion, we have studied about the particle in a ring problem, its Schrodinger wave equation, different solutions, expression for energy, wave functions, etc. That all about the presentation. Thank you.